that. My name's Mark Danson. I'm from Salford University, which is probably the most interesting university in Manchester. My title is developing the Salford Advanced Laser Canopy Analyser. I'm actually going to take a slightly different approach to Mick and Jan and take you a little bit further back in the development process to almost to the beginning of the idea of dual waveform laser scanning. Before I do that, I'd just like to say that almost all of the slides from this presentation were the result of one completed and one ongoing PhD, the first from Lucy Schofield and the second from Fadl Saseh, both of whom are in the audience. In addition to that, I'm going to do my acknowledgements right at the beginning because many other people in the audience will recognize bits of work that they did as well. So I thought I'd just get that over and done with. It's quite a long list. Rachel Galton, Philip Lewis, Matt Disney, Steve Hancock, Oliver Gunniwan, Alberto Ramirez, Richard Armitage, Eric Casella, John Murray, John Armston, and Alan Strahler. And I hope I haven't forgotten anybody. I should have named everybody in the room. That would have been safer, wouldn't it, really? This is what SALSA looks like. I call it an experiment, not an instrument, because it was never designed to be an instrument for operational applications. It was designed as an instrument to allow us to explore the potential applications of dual wavelength full waveform laser scanning. This is what the thing looks like. This is in the park just outside my building. This is Fadl on the right-hand side looking into the computer, trying to work out why it's not working probably at this point, I would imagine. A lot of people say, when I talk about SALSA, that I sort of describe it as if I was describing one of my children. Well, actually, my children are much better behaved than this instrument by quite a long way. So the motivations, I guess a lot of people in this room are aware of the motivations for trying to develop such a system up until the development of Dwell and SALSA 4 or 5 years ago. All instruments, or most instruments, were single wavelength. They used scan geometry, which was great for scanning buildings, but not very good for scanning forests. They invariably would record one return, or maybe a first and last return. They would not allow you to control the output and detection levels of the instrument. So, for example, our Regal 390 scanner that we used for a number of years before this saturated at very close range in forests and became, well, not useless, but less than optimal. We also found at that time we have no access to the instrument characteristics, so it took us about 5 years for Regal to tell us that the beam size that the instrument was 20 millimeters. And also, as people will be aware, it's very difficult to get access to the guts of the instrument, actually find out how it works. So they're the motivations, and in developing the concept, we addressed each of those motivations in a particular way, starting with having more than one wavelength, trying to design an instrument that was suitable for scanning forest canopies, to try to collect full waveform data, to access the optical pathway so that we could tinker around with the signal and make it, optimize it for a particular environment, and also to take the leap of faith and just acquire the binary data that allows us to start from scratch with data processing and analysis. So just very quickly, this is how it all happened, really. The origins of the instrument really go back beyond or before 2008 to a meeting in China where I think Alan was there, actually. It was a spectral signatures meeting, and I saw a fantastic talk by David Jupp talking about the echidna instrument and the amazing measurements that could be made with echidna. And at that meeting, I was also talking to Philip Lewis, who many of you know, and I said, well, we ought to have one of these somewhere on this hemisphere, possibly. Why don't we try and make one? And he said, oh, that's a waste of time. We'll just borrow the Australian one. And I ignored him. Normally he's right, but on this occasion he was wrong. And so I started to think about trying to develop this instrument. I was very lucky, actually, to get a little bit of money, £30,000, in 2008. And at that point, I got in touch with a company called Halo Photonics. And they are a commercial company that we'd worked with for a long time, but they build atmospheric profiling LiDARs. So these are instruments that you put in an airport, and it scans 24 hours a day and measures a three-dimensional wind field. And their instrument looks like this. And I said to the chap who runs the company, maybe we could adapt that and build a thing to scan for us. And he said, yeah, of course we can. He was a physicist. They always say yes. And he said, well, here's our device. Maybe we could use this. And what you may not be able to see from the back, but if we use this scanning device, there will be a hole in the middle of our scan, which was about 1 meter wide. Now, that doesn't matter at 3 kilometers when you're scanning the atmosphere, but it matters if you're scanning a 20-meter tree canopy. So I wrote to him in early February 2009, and I said, I've drawn this thing on the back of an envelope, literally was on the back of an envelope, and I said, here's your current design that gives a hole in the scan. Why can't we build it like this, and then we can get a complete hemisphere? So I said, possible new design to locate beam at center of rotation of scanner head. I've just slagged off physicists, but literally by the end of the month he came up with this idea. So this was a new scanning mechanism which allowed us to start to build the instrument. In December 2009, this is what it looked like on his carpet. This is just the body of the instrument, and actually most of the development costs were to do with the box and the motors and the scanner. The actual laser components are actually relatively inexpensive. In February 2010, the instrument looked like this, and the story continues. So in April 2010, the instrument arrived, more or less at the same time as Rachel Galton, I think, arrived to work on this with me. So on this slide, you can see the instrument as it looked then. I've been digging through the archives of emails and bits of document, and I think this is the first waveform that we ever recorded from the instrument. So you can see here the 1545 waveform. This is a composite of a dozen or so waveforms. This is part of the reflected outgoing pulse that's used to zero the instrument, and this is a nice return probably from the wall of my building. This is one of the very first scans that were recorded, and you can see it looks a bit of a nightmare, as these things always do at the start. You see on the left-hand side of the hemisphere there's apparently a whole load of features at very close range, but suspiciously only for half of the hemisphere. And this was retro reflection of the outgoing beam back into the instrument, because the glass cover on the front of the instrument was perpendicular to the beam. So we had to whip it off and use cardboard to stick a glass window at a slight angle so that we didn't get this retro reflection. So Rachel and I worked very hard. Well, actually, Rachel worked very hard for 12 months. And in the development of the algorithms for this instrument, we had a second laser wavelength fitted, 1063, in April 2011. This was the first scan I could find recorded with both wavelengths. So I'm not going to go through all the details. The details are already published about this instrument. Now I've sort of looked at this and heard Jan and Mick's talk. This is a bit basic, really, but I wanted just to try to reinforce this dual wavelength concept for people who are not entirely living with it on a daily basis. So here we have an object, a square grey object which has a reflectance that we measure with a laser scanner. And with a laser scanner, the red blob is supposed to be the beam footprint. And from that, we measure an intensity. And in this case, the beam fully occupies the object, or the object fully occupies the beam, I should say. And so we could say that with a few assumptions, the intensity at this wavelength is proportional to the reflectance. If we measure that same object, but only partially hit the object's reflectance stays the same, of course, but the intensity is reduced, and we can calculate that as being related to the reflectance of the object and the area that's illuminated. And in the third example, you can see, or you may not be able to see, it's sort of deliberate, we have a beam which only just touches the edge of the object, and now the intensity is much lower. So we're measuring the same object, but because we're not seeing all of the object in a particular footprint, the intensity that we record is different. Now let's say we've got an object that we measure at two different wavelengths, let's say 1063 and 1545 nanometers, just for the sake of argument. In the top example, you can see that, I don't know, just under half of the beam footprint is intercepted by the object, and so the same relation applies. The intensity is proportional to reflectance times the area. And in the other wavelength, the object has a different reflectance, but the intensity is proportional to the reflectance at that wavelength and the area. And of course, if we take a ratio, then those areas disappear, so that the ratio of the reflectances is no longer a function of the area. So the ratio, which we use, the normalized difference index more often than not, is not sensitive to the amount of material in the beam. So I'm just going to animate this. It doesn't matter where the beam falls. The ratio of reflectances should remain the same. So that's really a sort of cartoon version of what we're trying to do here. So in terms of the data, this talk is warts and all, as they say. This shows the lowest level of data that we record with the instrument. So here we have a bin number or range. We can convert that to distance. Each bin is 15 centimeters in range. And here we have the raw DN that we record on the instrument. And what you can see here is an outgoing pulse of the 1545 laser, a load of noise, and then a nice clean return. A load of noise, and then here we see the outgoing pulse of the 1063 wavelength, and at the same range, nice clean pulse for the 1063 laser. So one difference between Dwell and Salsa is that Dwell records the two wavelengths simultaneously, and Salsa records them sequentially. And we worried about that a lot, for a long time actually, that of course, you know, in the very small amount of time that light's traveling that distance, that there may be a displacement of the footprints. Now that's still true, of course, but there are many other things which are a much larger effect in the measurements that we worry more about these days. So what I've done here, what we do to process the data is simply to split the waveform into the two wavelengths and stick them together. So this is the 1545 nanometer wavelength shown in a bit more detail. So the data processing algorithms are very, very simple, and they are open to further developments and refinements. And if anybody wants to try, there's no problem. We'll give you plenty of data. So we apply a noise threshold, and then we measure the range. So we measure the range using the bit of outgoing pulse that we've just seen from either wavelength, and we measure to the center of gravity of the return pulse. So sort of reflecting back to this morning's conversation a bit, we can measure X, Y, Z. So all we have to do is know where the instrument is pointing, and that, with the range, that gives us an X, Y, Z position. That sounds trivial, but Steve Hancock spent a very large number of hours trying to make sure that those X, Y, Z coordinates were in the right position, and did a fantastic job, and we're pretty confident that they're quite good now. What else can we measure? We can measure the intensity sum. So our algorithm for measuring intensity is simple. We look at the bins above the noise threshold, and we add them up. So here, in this example, we've got 3 bin measurements, and we just add the intensities in those 3 bins. We've got the waveform width, and again, our approach is simple. In this case, we've got a waveform width of 3 bins. We can measure the return number. Here we've got the first return, but this could be the first of many returns, up to 7, 8, 9, 10 in some of the measurements that we've made. We can, as you'll see shortly, convert this intensity value into apparent reflectance. And finally, we can measure a reflectance ratio of some sort. So what does the data look like? Well, this isn't SALSA data. This is just a photograph. But it shows the site. Doesn't look quite that good. Don't get too excited. This is an example of some data I collected just before Christmas at a site in the Lake District, which is the northwest part of England, just on the border with Scotland. This is a Forestry Commission plantation called Lindsay Green, a mixture of different species, beech, oak and birch. And the data I'm going to show you on the next slide is a full resolution scan. So that means 9 million separate waveforms in 2 wavelengths, where each waveform is made of 15 centimetre bins. And in this case, we're measuring out to 60 metres. So the maximum range of the instrument is 105 metres, but generally the signal is quite low at that range, and we often restrict the data to the first 60 metres. So this is a full resolution scan recorded quite slowly in something like 170 minutes, something like that. So on this slide, we've really got a summary of the sorts of information that we can extract from SALSA data, but in fact, we can extract these sorts of data from many different types of instrument. So the colours are all over the place, but I'll just say briefly what each one means. So top left, we've got the range. So the hotter it is, the nearer it is. In this case, I've just plotted all the returns that we measure, but we can easily just pick out, for example, second returns. So now on this figure, you can see second returns, and many of the points on the tree stems will actually be second returns from the stem, because the first return was from material in front of them. So we've got a lot of information in terms of the return number from these data. The traditional measurement, uncalibrated intensity, which 99% of people using TLS will use. The bottom left-hand side, we've got pulse width. So the red points are those which have wide pulses, and the greener and bluer points are narrow pulses. And then bottom right-hand side, we've got apparent reflectance. This is 1545 nanometers. So this is after the application of our radiometric calibration approach. And I'll forget to say it later on, but I will point it out. One of the things that you can see here is that in the distance, you can see some red trees which appear to have an anomalous reflectance, and they're beyond the range of our calibration approach at the moment. So they're normally beyond about 40 meters from the scanner. And then finally, this is the normalized difference index that we've heard about before. So this is a leaf-off scan that was recorded, as I said, about just before Christmas. So if the bark or wood material in this stand was homogeneous spectrally, then we would expect the normalized difference index to have the same value throughout. So it actually looks pretty boring because there's not a lot of variation. The main variation you can see actually is this area here with blue NDI, and this is a branch of beech, I think it was, that had very, very dry leaves. So these dry leaves appear to have a quite significantly different normalized difference index value than the rest of the stand. So I just want to take a few seconds to highlight some successes. This is work that's been going on for a number of years, but I've summarized it here. So with Lucy, we worked on the calibration of the instrument, and one of the problems that we encountered very early on was that lasers heat up and cool down, and as they heat up and cool down, the intensity that they record changes. Many of the commercial scanners are very well cooled and operate very quickly, so you don't notice this. But if you scan over a long period of time, this is laser temperature versus intensity for a number of different reflectance panels. So you can see the intensity dropping off. So we used a black box approach essentially and used in situ field calibration panels to derive a radiometric calibration based on neural networks. And the outcome of that is that we reckon we can calibrate reflectance to of the order of 5 or 6% within the range that we've derived the equations for. This is Rachel's, or a paper that Rachel led on, where we were looking at water content estimation. So a byproduct of the two wavelengths that we use is that the ratio is sensitive to the amount of water in vegetation. This has been known for a long time, and in fact I worked on it in the 1980s by using spectral data to measure the reflectance data to measure water content in vegetation. But just so happens we've got the right wavelengths to do this. And we end up estimating the leaf water content in this laboratory situation to pretty high accuracy. So this is root mean square of, 0.07 grams per centimetre squared with SALSA. So we count that as a success. This is a new paper, actually, which Steve Hancock has led on. We heard in the previous talk a little bit about view angle effects. And so Steve worked on this experiment with SALSA to look at the view angle effects of individual leaves. A bit hard to see on the picture here, but you've got a series of leaves on a rotating panel here. This is the variation in reflectance with view zenith angle or incidence angle for the two wavelengths, and this is the normalized difference index calculated for those two wavelengths. So we're hopeful that going forward we've got a good way to account for these variations in view angle. Well, we've heard a lot about dual wavelength classification of forests, and we've been trying to do this as well. It's actually much more difficult than Jan alluded to, and there are a number of different steps which are required. So, for example, we have to get good apparent reflectance product. We have to match the returns because there aren't returns in both wavelengths for every object. Calculate an NDI, and then use some way to separate the points which are leaf and bark. And there are actually a number of different ways to do that. Thresholding the NDI, thresholding apparent reflectance or intensity, or the spatial classifiers that we've heard of. But once we've done that, once we've separated that, we then have the potential to estimate true leaf area index, leaf area density profiles, and leaf phenology, and then get information on wood volume and biomass. The picture at the bottom just shows two examples of that from John's site, actually, in the Lake District. This is one tree in an isolated tree in a field. This is the wood mapped using a 1545 threshold, and the leaves, tree together, NDI threshold, leaves, and then the two things together. The problem is, when you eyeball it, it looks quite good, but who knows? Who knows if that's really good or not? The only convincing evidence I've seen so far is from Lucy's PhD, where she worked in a number of different test sites at a site near Manchester. And she used the leaf-on mapping of leaf and wood to produce these images for 5 different stands. So this is 1545 wood, leaf, NDI, wood, leaf. That's a single tree picked out. But cleverly, what she then did was take the thresholds that she'd used for the leaf-on data and apply them to the leaf-off data. So if the thresholds were dead right, then the leaf-off scan should consist only of wood. But of course they didn't. But these show the error estimates. So 79% of the points in the leaf-off scan were erroneously classified as leaf here in plot 1 with the 1545 threshold. The lowest value, the lower values are for NDI, you can see. So it looks like using the NDI is actually better than using a threshold of the 1545 nanometer channel. And the lowest error that we got was in a pure standard beech, where the spectral properties of the leaves and the bark were quite different. Okay, so next to last slide, I think I've got a couple more minutes. These are the recent candidates selected by Donald Trump to advise him on his political policies, otherwise known as the gremlins. So here's a slide of gremlins. There are a number of gremlins in here which you may or may not have noticed as we've gone through. Beam alignment, we've already heard about. That's a big issue. But actually, when you're designing an instrument, it's very difficult to make the beams the same size. So if you buy lasers off the shelf, then they have particular characteristics. We have lasers which have a difference in diameter of 1 millimeter at the exit. So there's a significant, small but significant variation in the size, but we also have the problem of alignment. You might also have noticed that the normalized difference index appears to go beyond +1 and lower than -1. And this is because sometimes we get negative reflectance values. So if our radiometric calibration is not spot on, the negative reflectance values that we get cause an anomalous NDI value outside the range. Lucy will tell you more about this, but we sometimes get silly high values in our scans, and that's because our algorithm uses a simple noise threshold, and it regards these separate returns from closely spaced objects as one single return, so we get a very, very high intensity value. So anybody who wants to play around and try and find a better way of doing this, as I said before, very welcome to have a go. Ringing is also a problem. This is an electrical response to very high intensity returns where the instrument bounces up to a high level and then bounces below the noise level and bounces back up again in a fashion like this. The effect in the data is you see ghosts, ringing ghosts behind trees. We have a very simple approach to remove this, but clearly there are many different ways to do it. So this is my sunset slide. It happens to match the Royal Society banner quite well, I thought. Quite by accident, but there we go. So this is the sun setting on my laser scanner measurements in the Lake District. One thing, another gremlin in here, actually two gremlins. Don't stand in the way of the laser scanner, otherwise your head appears. I think this is a sort of sunset picture, but it sounds a bit corny now to think about. This is the dawn of a new era for terrestrial laser scanning. And actually, I thought maybe, when I came yesterday, I immediately thought the title of the meeting's wrong. It should be the Terrestrial Laser Scanning Revolution in Ecology ? I'll leave it there. Thank you very much.